Physics Notes, Unit 22, Part C. Magnets, magnetic fields, magnetic forces. Once again, I can't stress this enough. Magnetic fields are created by a moving electric charge, proton or electron. That field around the proton or electron is circular. Like in the previous unit, when that circular magnetic field interacts with another linear magnetic field, you get a force. Same thing happens here once again in this unit. We have a long wire. And here's kind of a little sample of what happens. A wire with a current, it's a moving charge, like an electron moving in a straight line. There's a magnetic field around this wire. If I look at this diagram, there's a magnetic field around that wire that is circular. All right? Between the two poles of this horseshoe magnet from north to south, it's a fairly uniform linear magnetic field from N to S pointing straight across. So when you have a circular magnetic field around a wire that's interacting with a linear magnetic field between the poles of a magnet, you get a force that's perpendicular to the motion of the charge. You end up with three things that are perpendicular, mutually perpendicular: the direction of the current, the direction of the magnetic field, and the direction of the force. Same thing is true whether this wire is replaced with a proton or electron. Same effect. Forces that are perpendicular to motion create, for a free charge, it will go in a circular motion, but for a wire is restricted, so it just kind of bends like this, like the force will bend the wire up or bend the wire down, following the right-hand rule. It's going to be very, very similar to F equals QVB. It's a cross product, F equals IL cross B. But instead of putting the cross product in there, I put the sine of theta. That's what cross product is. The angle in these problems will all be 90 degrees unless you're told otherwise, and then it's obvious. If it's 80 degrees, you plug in sine of 80, which just kind of reduces your answer by just a little bit. So once again, we'll be using the right-hand rule. Taking your palm as a stiff right hand, with your thumb sticking out and your fingers in one direction. Your fingers will still be in the direction of the magnetic field. Your thumb now will be in the direction of the current. That's the idea of something moving, but your palm is still the force. So the only thing we're really changing is instead of V, you have I. Now I'm using the same diagram, so if I come to this diagram here, I'm going to change this letter right there to an I. That's the current. So that's the only thing I'm changing. Your thumb is now the current, so change that to an I. Change that to an I. And let's practice the right-hand rule. All right, three mutually perpendicular vectors. Here's a diagram. My final diagram will still always be that circle with two vectors. So for A here, you have a magnetic field that's toward the ceiling. So that dot there means a magnetic field that's toward the ceiling. Come on. I don't know why it's doing all this. There we go. Oh, it's not doing something. All right, so magnetic field towards the ceiling. And we have a current that's toward the south or towards the bottom of the page. So I'm going to call that B, magnetic field towards the ceiling. And this is the current, I. So what we're missing is F. So that diagram I just did, it goes with the problem above it, part I. Maybe I'll put it up there. So sorry about that. I'll draw it again so it doesn't get mixed up. So we have B towards the ceiling, current I towards the south, towards the bottom of the page. So my answer is going to be to the right or to the left for the force. But what I do is I take my right hand real stiff. I have to point my fingers toward the ceiling, towards the sky. Have my thumb pointing behind me, towards me or behind me, towards the back of the room, and my palm faces to the left. So the answer to this problem, the force on this wire, will be towards the left, towards the west. All right. Let's do letter B here. Okay, you're getting the hang of this, I hope. You should start off by drawing a circle. That's what we're looking for in this case. I have B and I. I'm looking for F again. I've got I, the current, this way, towards the north, or towards the top of my page. I've got B towards the east or to the right. So I'm looking for F in this circle. So the question is it a dot towards the ceiling, or is it an X towards the floor? So I take my right hand. All right, I have to have my thumb point towards the front of the room. So I rotate it turns out that my palm is going to face flat down. which will be the answer, because I have to have my fingers pointing towards the right. My thumb has to point towards the front of the room or towards the top of the page of this paper, if the paper is laying flat on my table. And my palm points towards the floor, so that is going to be an X. The nice thing about these is there's no negative case for negative charges. When you have electrons, that's why the F equals QVB is a little bit trickier when you have an electron, because you got to change your last answer. Or another trick is to use your left hand when you're using an electron. If you want to try that, whatever works for you, that would be a legitimate technique. 2 more practice problems for right-hand rule. Okay, so start by drawing. So we have a velocity vector towards the floor. So for part C, we have velocity towards the floor. Okay, so that's the velocity. Oh, I'm going to make that a current though. So that they change that. That's I, because these are supposed to be examples with wires. So, but it's current towards the floor. It replaces velocity. Okay, so I got F to the right. F to the right. So magnetic field is either towards the bottom of the page or top of the page. So it's either towards the top or bottom. It's got to be perpendicular to F. So I have to take my my palm has to face the right. My thumb has to face the floor. My palm has to face to the right. My thumb has to face to the floor for the current. And my fingers, okay, if I kind of twist my hand a little bit, my fingers point towards the front of the room. So B, magnetic field is towards the front of the room. All right, last example. Hopefully that bird in the back, I have a bird outside my windows making a bunch of chirping noises. I don't know how much that's in the video here or the audio, but last example. We have B towards the ceiling. We have F towards the back of the room. The force on the wire. So the current on the wire is either left or right. 2 answers. So I take my right hand. I have to have my fingers, which are the B field, towards the ceiling. My palm, for the force, has to face the back of the room. So if I do that, my thumb, which is the current, has to be to the right. So the answer is this way. That's my current, or the answer. All right, so that's a review of right-hand rule for force on a current-carrying wire, straight current-carrying wire. And now for just the basic entry level force on a wire, F equals I L B sine of 90, which I leave off. I use a capital L. A lot of the books use like a cursive L, but I have a hard time with that, so I use capital L for the length of wire. It's pretty obvious. So they're giving us the force here in this problem, 4.8 newtons equals, we're trying to find the current. This is straightforward. Length of wire, 0.32 meters. And B is 850 milliteslas. That's 0.80850. Got to move it 3 places for milli, 2 places for centi. So that's a pretty much straight plug that in. You get 18 amps of current in that wire. It doesn't give us the geometry of that, but we just practice right-hand rule. So that's straightforward. You'll need to be, using that equation in these more advanced problems that are more of a vector nature. Here we go. Because once again, these forces, these are all vectors. Direction is very important. Now we have an interesting situation. 2 parallel wires of that length. Let me draw this for you and explain what's going on here. So here we have 2 parallel wires. Let's say they're laying on this paper. They're laying flat on a tabletop. They're 1.5 centimeters apart, very close, but they're 25 centimeters long. I didn't label that yet, but it's in the description up here. They're carrying 2 different currents. So this one's a pretty involved problem. There's a lot going on here. Let me scroll down a little bit. So what happens is each wire creates a magnetic field due to the current in that wire. So there's going to be 2 magnetic fields here. There's going to be 2 interacting circular fields. The net result, before I prove this, the net result is if the currents are in the same direction, which they are in this case, the 2 wires are going to attract each other. And that's what we're going to calculate here. And I'll show you a shortcut once we're done. But So this is kind of diametrically opposed to, you know, the standard rules where opposites attract. Here you have if two wires have the currents in the same direction, they actually are attracting each other. And if there's no friction, they would slide together. You're laying on a tabletop. And they're connected to something. They're just not two little pieces of wire sitting there, but they're connected to something that causes the current. So then if they attract with the currents in the same direction, which is the case here, if they have currents in the opposite directions, they repel. You can just memorize that. But I'll go through the right-hand rule to show you that. But bottom line here is each wire has a magnetic field. I'm going to start with the 20 amp wire. I'm going to call that wire number 1. Let me switch it up here a little bit. I'm going to call that number 1. That's number 1. And then this is wire number 2. I can call them the 20 amp and the 5 amp wire, however you want to label those. But the 20 amp wire, if we go back to trying to represent the magnetic field around that wire, the magnetic field around that wire would be represented like this. This would be on the right-hand side. It has magnetic field going into the paper. Actually, I'm going to erase 2 of those because I just want to look at one of them. I could draw more of it. But the other thing is it's getting weaker with distance. And weaker with distance. So all of that I just drew there is the magnetic field from wire number 1. And on the left side, I really don't care about that because that goes out here in space. It does not affect wire number 2. So wire number 1 has a magnetic field that then hits wire number 2. So how strong is wire number 1's magnetic field at the location of wire number 2? Well, I can just use this is one of the original equations I gave you. The magnetic field created by a wire. I'm going to call that 20. I'm going to say 20. From wire number 20 is mu 0 over 2 pi I over r. So what I'm interested in is the magnetic field from wire number 20, created by wire number 20. That's 2 times 10 to the negative 7th, times the current in that wire, which is 20 amps, divided by how far I am from that wire. That's 0.015 meters. So the magnetic field that wire number 1 creates at that distance, and it's stronger if you're closer, if it's weaker if you're further, but that comes out to be 2.7 times 10 to the negative 4th Teslas. So that wire, that field, hits wire number 2, and you could draw more of those. I'm going to draw them and then erase them because it gets messy, but I could keep drawing that X, 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 okay, and X. So all of this is the magnetic field representing the tangents to the circular magnetic field that goes around wire number 1. And all that magnetic field is hitting wire number 2, all along wire number 2. I'm going to try to erase all of that for now. Let me see if I can erase some. Maybe I can't erase all of that. I've got a lot to erase now. All right, anyway, we'll get there. Sorry for all the tapping. Okay. Whoopsie, I went too far. So let's go back here. So it was 2.7 times 10 to the negative 4th Teslas. Now I can use the equation F equals ILB, sine 90, to figure out the force on wire number 2, the 5 amp wire. So the force on wire number 2, the 5 amp wire, is the current in that wire, 5 amps, times its length, which it told us what was the length of that wire. It was 25 centimeters. 25 centimeters, if you look up there, 0.25 meters, times the strength of the magnetic field that's hitting that wire. Well, that's being hit. It's not being hit by its own magnetic field. It's being hit by the magnetic field of the other wire. That's the key here. So the force on the 5 amp wire is 3.4 times 10 to the negative 4th newtons. 3.4 times 10 to the negative 4th newtons. Okay. Calculate the force they exert on each other. Well, that's the force that wire number 1 exerts on wire number 2. But we can use Newton's third law. We can use Newton's third law. It says if wire number 1 exerts that force on wire number 2, then wire number 2 exerts that force on wire number 1. So that's the answer. That's the force they exert on each other. That is the answer to answer A. Okay, I didn't give myself enough space here, but let me show you something here. Bottom line is there's going to be a shortcut because there's going to be a lot of problems like this. We have another one coming up here in a second, and there's going to be a better way to do, well, a shortcut. Bottom line is if we take that equation F equals ILB, if we take F equals ILB. So that was the force on wire number 2, the 5 amp wire, the force on the 5 amp wire was the current in the 5 amp wire times the length of the 5 amp wire times the magnetic field from the 20 amp wire. So that's the tricky part there. That's what I just did way over here on the right. Those are all 5s if you put them, well, except for B. B is 20. I calculated it first. Well, B20, if you go back up to the top, is the current in I20. Okay, so up here now, B for 20 is mu 0 over 2 pi I20 over R. So I'm going to plug that in. I'm going to plug all of that in, circle that, bring it down here for I20. So you get the force on wire number 5. I'm going to generalize this in a second. Simplify and generalize. Is the current in wire number 5 times the length of wire number 5. And by the way, if the two wires are different lengths, they have to be parallel wires. They have to be parallel wires. You take the shorter one. You take the length they have in common. Take the shorter length. Times B20, which I'm plugging in mu 0 over 2 pi I20 over the separation distance. That's how far apart they are. So I don't need to call that R5 or R20. That's just how far apart they are. That's an R right there, not a V. Well, bottom line is the generalization. Okay, instead of calling this 5 and 20, I should have stuck with 1 and 2. So if we make all the 5s a 2, and then the I20 is wire number 1. Bottom line is an equation that's going to be very useful. Force between parallel wires. In general terms, rearranged. It's mu 0 over 2 pi. If I bring that factor out front, because all of these are multiplication. So I'm going to rearrange that equation. It turns out, so in this case, you'd say I5 times I20, but in general, I'll just say I sub 1 times I sub 2. It's the product of the two currents. Okay, times the length where they overlap. I don't need to call it length 5 or length 20. That's just they both have the same length, 25 centimeters in this case, all over R, how far apart they are. So this equation right here is very powerful. You're going to want to circle that. That's the force between parallel wires. Force between, that's not how you spell between. Okay, B-E-T-W-E-E-N, parallel wires. If they're carrying current. So, but they both have to have current. If they don't have current, then the force is 0. So that's a shortcut. We could have just plugged into that equation right up, and that would have given us the force of, and they attract in this case. These I circled that at the top. They attract. Okay, so that's the force of attraction. Now, let me prove that they attract. For example, if I go back and use the right-hand rule, I'm going to go back down to wire number 5. So if I look at wire number 5, here would be the right-hand rule diagram for wire number 5. There would be the blue X that's already on wire number 5. And then the current goes this way. That's the current, 5 amps towards the top of the page. So that's I, and that's B. Okay, that's I and that's B. So then the force is going to be to the left or right. We think it's going to be to the left. Let's double check this. So if you take your right hand, we're practicing right hand rule, then your thumb has to point towards the top of the page, and your fingers have to point towards the floor, because B is your fingers. So if I take my right hand, my thumb pointing towards the top of the page or the front of the room I'm in, that's the arrow for current, my thumb, towards the floor. My palm points to the left. So yes, indeed, the force does come out to be the left. Okay, and if you do the same thing, you apply the right-hand rule to the other wire, the force comes out to the right. And it has to, because it has to also be consistent with Newton's third law. They attract each other with equal and opposite force. All right, so you can pause that and take a picture, because I need to erase that to do part B and C. Actually, B and C, there's a lot here. I should have left some space here. You might need an extra piece of paper. Sorry about that. So part B is definitely a vector problem. I mean, all of these are basically vector problems, but now we're looking at this location on this dashed red line, which is 0.75 centimeters from each wire. It's half of the 1.5 centimeters. And once again, the green here represents magnetic field, the tangents to the circular magnetic field that's going around wire A. That's using the right-hand rule number 2. You can go back and practice that. And the blue would represent the magnetic field around wire number 1. And I don't care what's happening to the left of wire number 1. I really don't care what's happening to the right of wire number 2. But what I care is what's happening along this line right here. But the tangents to the green magnetic field are towards the ceiling, towards the sky. And these blue axis represents the tangents to the circular magnetic field in the plane of the paper. So at that moment, it's toward the floor, tangentially toward the floor along that line in the plane of this paper. So one is down towards the floor, one's up towards the ceiling. So they're diametrically opposed. If they were the same size, if they were the same currents, then those would cancel. But the blue magnetic field, and by the way, we call that flux. You don't need to know that for this class. Well, maybe in the next unit. It's called magnetic flux. So yeah, you don't need to know it for this unit, but next unit. Magnetic field. It's magnetic field strength. It's toward the floor. And I can calculate the size of that, like I've been doing. And I'm going to switch to, basically, I'm going to calculate for both wires and have two vectors. So for, I'm going to call it B20. And I did it at the 1.5 centimeter mark earlier because I had to go all the way over to wire number 2. But now it's just mu 0 over 2 pi I over this distance. So at that location, okay, it's 2 times 10 to the negative 7th. Times the current in that wire, which is 20 amps. Now it's 0.75 centimeters, which is 0.0075 meters. So you could verify that. So half of 1.5 is 0.75, and then move the decimal 2 places. So the magnetic field strength tangentially at any circle in that distance from that wire is, I believe, 5.33 times 10 to the negative 4th Teslas. 5.33 times 10 to the negative 4th Teslas. That's the strength of that magnetic field towards the floor. Well, I can do the same thing for the green, B sub 5. It's going to be the same computation, but it's going to be 2 times 10 to the negative 7th with one change. It's a 5 amps instead of 20 amps. So it's the same distance. Bottom line is you could take 1/4 of that previous answer, or you can just recalculate everything. It's 1/4 of that, which is, if you do the math, it's 1.33 times 10 to the negative 4th Teslas. That's toward the ceiling. So I need to add those two. Well, adding those two is really like subtracting. Is one's towards the floor, one's towards the ceiling. Which one's bigger? So B total, B final, is going to be the bigger one, 20, minus, that's minus B5. So it's going to, and they both have the same exponent. So I can symbolize that, and B20 is 5.33 times 10 to the negative 4th. I'll add that back in, or put it back in there, minus 1.33. I can subtract those two, they have the same exponent. So the final answer, the B total, at that location is, what, 4.0, or 4.00 times 10 to the negative 4th Teslas. And I need a direction on that. It's toward the floor. Or I could just put it like this. Here's my answer. That means toward the floor, X. That's understood. Toward the floor. So that's the net magnetic field midway between the wires. And you could pick any location. Any location. I think one of the ones in the homework asked you to go closer to one of the two wires. Or actually, part C here, where would the magnetic field be? 0. But bottom line, if you're not midway between the wires, which we're not going to be now, then you're not going to have 0.0075. They've got to tell you where you're at, how far away from each wire you are, and recalculate each of these, which we'll do in part C here. Although we're going to take a shortcut in part C. So I'm going to erase this again and set up part C. So pause it if you want to write that all down if you haven't. Okay, so I've done a little setup work here. And we've had some problems sort of like this with electric fields and electric forces. These are magnetic fields right now. So the answer is going to be somewhere along this dashed line right here, this blue dashed line. But you have to be closer to the weaker wire, because as you get further from the stronger wire, the magnetic field lessens. The blue magnetic field lessens as you get to the right, towards the weaker wire. And when you're closer to the weaker wire, the green magnetic field is stronger, so they can be equal. At the midpoint, the blue magnetic field from wire number 1 is stronger. That's what we just determined. So we got to go to the right. So the answer is over here somewhere, along that line. Well, we want B20 in magnitude to be equal to B5. The magnetic field from wire number 1 equal to the magnetic field from wire number 2. So basically, if we symbolize that, it's mu 0 over 2 pi. Okay, I sub 1, well, let me just put them in some, I20 over, I'm going to call that distance R, or we could call it R1. I could call it R1, or I just call it R, because if I just call that R, that's a distance that we want. Then the other remaining distance right here, I mean, I could call it R2, but it's better that you could just call it 0.015 minus R. So I don't have to call that R1 or R2. That because the total distance is 0.015 meters, 1.5 centimeters. I take the total distance minus this R, gives me that other distance right there. So I could call it R. I could call this R1 and call this R1. Doesn't really, you don't need a subscript there. Okay, equals mu 0 over 2 pi I5 over the distance. Once again, I can call it R2 if I want to, but that would be we need to get rid of it anyway. But I don't want an extra variable there, so it's 0.015 minus R1. Now, if you look at this, it looks a little, it might be difficult to solve, but it's not, because this and this will cancel, and it makes it really simple. I mean, you end up with, famous last words, if you cross multiply, well, I20 is 20. So I'm going to plug the numbers in here. I20, so I'm going to take I20 up there and multiply it by cross product, or, well, it's not really a cross product, minus R sub 1 equals, going the other way, R sub 1 times I5. I5 is 5 times R sub 1. So I plugged in a 20 for the current, because I knew I should have put that in to begin with. There's a 20 there, so I take the 20 times this binomial, just crossing the two fractions there. You should be able to do that. Anyways, 20 times that, let's see, I did the math here earlier, and I got 20 times it's 20 times 0.015. I mean, I didn't do it. Hang on. All right, so I did all the math. 20 times 0.015 is 0.3. Distributing, 20 times negative R1 is minus 20 R1 equals 5 R sub 1. Add the 20 to both sides, you get 0.3 equals 25 R sub 1. R sub 1, the distance from the wire number 1 is 0.1012 meters. And that makes sense because the distance to the other wire then would be 0.003. Okay? In other words, you didn't have to do this, but R sub 2 would be 0.003 meters. 0.3 centimeters, because that has to add up to 0.015. You have to be 4 times further from the stronger wire because it's got 4 times the current, and then 0.012 is 4 times as big as 0.012 is 4 times bigger than 0.003. So the answer, where on the plane of paper, it'd be 0.003 meters left of wire number 2, or 0.012 meters right. You didn't need to give both answers, of wire number 1. And it's consistent with a total distance of 0.015 meters. All right, here we go on the next one. Given the following 3 wires. Now these are supposed to be 3 wires. They're like telephone poles standing vertically, like fence posts, vertical wires. And you got an overhead view. And I haven't given you the direction of the currents, but it says this one is, well, my notes, is towards the ceiling. This has current towards the floor, current towards the floor. All right, I'm going to do this problem twice. That's why I have the diagram twice over here. Okay, so those are 3 wires, and it says calculate the force on each one. So we're going to use the shortcut equation. The shortcut equation being the force on a wire the force on a wire, two parallel wires, is F equals mu 0 over 2 pi. I proved this to you a little bit ago. Whoops. Times the product of the currents, I sub 1 times I sub 2 times the length of the wires, all over how far apart they are. We've done problems like this before with electrostatics. And the diagram is very, very important here. And it's going to be a lot of work. So hang on. I'll do these in pairs. So the 8 amp wire and the 6 amp wire, they have currents in the opposite direction. One's towards the floor, one's towards the ceiling. Opposite means they repel each other. So they have, to show that, I'm going to call that F1 and F2. They repel. F1, F2. Doesn't matter which one you call F1, F2. But I'm going to call F1 and F2 equals mu 0 over 2 pi times 8 amps times 6 amps times, it says they're 0.45 meters, divided by how far apart they are, 0.03 meters. So if you do all the math there, you get a force of repelling of 1.44 times 10 to the negative fourth, 1.44 times 10 to the negative fourth newtons repelling. But I have the repelling in the diagram. Okay, so then I can look at the 6 and the 4. The 6 and the 4 have currents in the same direction, so they attract each other. I'm going to call that F3 and F4. Very similar to an electrostatics problem we did. 3 collinear charges. So you can probably figure out how this will play out. The diagram, very important. So I'm going to do all the math here and then explain it. Hang on, let me pause. All right, so you might want to pause or just watch for a second and then write it down. It's very similar to the electrostatics problems we did. So you had to figure out the blue ones here, the 8 amp and the 6 amp wire, currents in the opposite directions, they repel. And the shortcut equation was mu 0 over 2 pi times the product of the currents times 0.45 over their distance apart, 3 centimeters, 0.03 meters, gives you that force in blue. Then I took the pair of the 6 and the 4 amp wires. They were separated by 5 centimeters, 0.05 meters, all in green down here. And I put this in the same exponent as the blue so I could add those eventually or subtract. 0.43, you could say 4.3 times 10 to the negative fifth if you want, but that makes them harder to add. And then for red, it's the two outer wires, the 8 and the 4. And they have currents in the 6 and the 4, the 6 and the 4 attracted each other, currents in the same direction, towards the floor. But the 8 and and I showed that with the green arrows pointing towards each other, they attract, currents in the same direction, they attract. The 8 and the 4 repel because they're currents in the opposite direction. 8 is towards the ceiling, the 4 amp is towards the floor. But once again, I plug the numbers in, the total distance is 0.08 meters. Gives you a very weak force because of the big distance. Nothing is squared though. And then I want to find out the net force on the 8 amp wire. Well, I look at the diagram and I've got it labeled real nice. I got to add the F1 and F5. F1 is 1.44. F5 is 0.36. With the exponents, I put that back in. So I can add them. That's 1.80 times 10 to the negative fourth. That's the exponent. Newtons. To the left, because the diagram shows left. And then the same thing for the 6 amp wire, the answer's to the right. I have to add F2 and F3. It shows me in the diagram. F2 is blue, F3 is green. I add the 1.44 plus the 0.43, 1.87 times 10 to the negative fourth newtons to the right. And then the last one's very small force because they're in opposite directions, I subtract it. And my mantra is, take the big force, the bigger one's the green one, to the left. Big force minus the small force. So F4 minus F6, instead of adding. So 0.43 minus 0.36 is 0.07. I put that back into standard, into scientific notation. The 0.07 times 10 to the negative fourth newtons would be fine. Same answer as 7 times 10 to the negative fourth newtons, but to the left. The bigger force is to the left. All right, so pause there, write that all down, because I'm going to reset this problem, part B. We don't have room. I'm going to erase a lot of this and do part B, which is a little bit different, similar concepts because it's a vector problem, but let me pause. Okay, so part B of number 6. each of these wires, same wires, and this one has, once again, the 8 amp wire has current going towards the sky, towards the floor, towards the floor. So each of these 3 wires creates a magnetic field that influences, exerts forces on the other 2 wires, as we did in part A, as we calculated in part A. So we have the net forces that we calculated in part A. All right, but now we're going to calculate the net magnetic field at a location 1 centimeter to the right of the 6 amp wire. So I'm looking at a location now where there's 3 magnetic fields. So we're not looking at a force. So we're looking at that location with that blue X right there. I'm not going to put a circle around it because I'm just marking that location with an X. Maybe I should just mark it with a dot. Well, it doesn't matter. I'll put the X there. So there's a location 1 centimeter to the right of that wire. Now, we're going to be using our basic magnetic field equation for the magnetic field around a wire. That is B equals mu0 over 2 pi I over R. We're not looking for a force now. We're looking for there are 3 magnetic fields that are interacting at that blue X from the 3 wires. I'm going to do these one at a time. So I'm going to do 3 calculations and then combine the 3 answers. It's a little bit easier than part A, at least mathematically. Conceptually, we've got to think about this. For example, wire A. Now, if we want to draw the magnetic field around that wire, we use right-hand rule number 2. And if we were to grab that wire with your thumb pointing towards the ceiling, you would get a magnetic field that looks like this. This is how it would look. It would be a magnetic field that circles around this wire like this. And I could keep drawing circles that get bigger and bigger. But I don't need all those circles. I'm going to erase some of these in a minute. What I need is one that's big enough, the circle that's big enough, that actually goes through that point X over there, okay, at whatever radius that is, 4 centimeters from wire number 8. And at that X right there, that field is in this direction, tangential to that circle. So usually our tangents look like, when the wire is laying flat on the table, then our magnetic field looks like X's and dots. But when our wire is perpendicular to the paper like this, our magnetic field is like the circles that it actually is. It's circling, so these blue lines represent the magnetic field around that wire. And now the tangent I just drew, I'm going to erase everything except for that tangent. I'll put the tangent back in there. But if I get rid of all those circles, because I don't need all that, it's going to clutter the diagram, but that represents all the magnetic field around that wire 8, and each of these wires will have a magnetic field. If I don't go too much, okay, I got rid of too much there. Okay, but bottom line is the magnetic field here. Whoopsie, man, get rid of that. The magnetic field, that last thing I drew was a vector that was tangential. I'm going to call that B8. The magnetic field tangential direction for those circles I just drew from wire number 8, so that blue vector there represents the magnetic field from wire number 8 and wire number 8 only. And now I just, to basically get the magnitude of that, that'd be I8 over R from 8. So I'm going to call that B8. B8 equals 2 times 10 to the negative 7th. What's going on here? I just lost something. Hang on. I think I got it back. 2 times 10, come on, times 10 to the negative 7th. Let's get this right. 2 times 10 to the negative 7th times the current in the 8 amp wire, 8 amps, over how far I am, 0.04 meters. So the magnetic field from wire number 8 is 4.0 times 10 to the negative 5th Teslas. Then I'm going to do wire number 6, B for wire number 6. It's going to be 2 times 10 to the negative 7th times 6 over 0.01. But before I calculate that, okay, for wire number 6, I'm going to draw this and then erase it. So what would the magnetic field look like? I'll switch back to blue again, and then I'll erase these. For wire number 1, I'd have to stick my thumb towards the floor, and the magnetic field would circle around like this. So the tangent for that one will be this way. That'll be B6, it'll be towards the bottom of the page. I'm going to erase that, except for that last vector. I'll put it back in. So B6, a tangent to the circular magnetic field around that wire, is going to be this way, B sub 6. And I calculate that down at the bottom. But before I calculate that, let me also just draw in for wire number 4. Wire number 4, the magnetic field goes like this. I can keep drawing those circles bigger and bigger and bigger, but if I draw one over at location X, the tangent will be in the same direction as B8. So I can draw, I call that B4. That's the tangent to those circles if I drew those circles bigger and bigger for the magnetic field. So that's the instantaneous direction, tangent to the circular magnetic field at that location. Switch back to blue, or to red. So B6 comes out to be 12 times 10 to the negative 5th Tesla. So I'm putting it in the same magnitude with the exponents. B4 is pretty easy to calculate because it's the same as B8, only it's half the, well, it's a 4 over 0.04. So everything's the same for it's half the current, so it's going to be half the answer, 2.0 times 10 to the negative 5th Teslas. So I've got to add up those three numbers, but I've got to be careful how I add those three numbers. Okay, because to get the final answer, if they're all in the same direction, I just add them straight, just add them. 12 plus 4 plus 2, which would be what, 18? But B total is going to be, actually B6 is the biggest. It's going to be B6 minus the sum of the other two, B8 plus B4, because B8 and B4 together are smaller. So it's going to be basically 12 minus 4 plus 2, ignoring the exponents right now. So that comes out to be, the final answer is 6, and I'll put the exponent back in, the power, times 10 to the negative 5th Teslas, and that's, I'll say south. Okay, towards myself, towards the bottom of the page. That's the final answer for the net direction of the magnetic field at that location. So it's fairly simple vector addition because they're not at angles. If you had angles, then you got to find components again. We haven't had to do that for a while, thank goodness. All right, so magnetic fields around current carrying wires. They're circular, they can interact, they cause wires to attract if they have the same direction of a current. We have one more problem left, but I think I'll save that for part D of this discussion since this lecture went kind of long.